Man, this biostat stuff is confusing. I don't get it.
Confounders, precision variables, mediators.
These are different roles that variables may play.
It's your bread and butter, baby, what's your jam?
Now I get it.
Welcome, Bio 6611, to the Introduction to the Wonderful World of Mediation Modeling. In this lecture, we're going to introduce the framework and idea behind mediation analysis, and end with a few extra notes and derivations that may be of interest. So let's jump right to it. What is mediation analysis? Well, it has to do with this idea of another role a variable in a regression model might play, which is a mediator. We previously discussed the idea of confounders and precision variables, and in this lecture, we're going to introduce the concept of a variable being a mediator, which we're going to designate by the letter M. This would be an intermediate variable on the causal path between an independent variable of interest, for example, treatment or some exposure, and our dependent variable or outcome. For example, we can use a direct acyclic graph here below, one of our nice DAGs here, but we see one difference from confounding is that the relationship of x, that exposure or treatment variable of interest, and the mediator m is that the arrow goes from x up to m. The information or effect flows from x up through m and then back to y. Different from the idea of confounding, where the confounder, which was c instead of m, was associated and affected x with the arrow reversing that direction. Further, this relationship can be broken down into two cases: an indirect effect, which is our arrow here going from x up to m through y, or a direct effect, which would be that case of x going directly to y without being mediated or going through m. In other words, it's the remaining effect after we adjust for or account for the effect of the mediator. Like we saw before with confounding, we have this idea of different models we can use to specify or describe the effect of mediation. Here we call them the fundamental models of mediation analysis. In the top left, we just have that generic DAG again that we are referencing here to just see and remind ourselves of the arrows in the direction they're going. But then we have the same model setup where we have a crude model, an adjusted model, and a covariate model, each of which serving this different role that will help us in different ways to calculate the summaries of interest, such as the indirect effect and the proportion being mediated through that m variable. When working in the context of mediation, we're generally interested in doing some form of inference. And using those three fundamental models for mediation analysis on the previous slide, we can draw that direct connection again to those three models we specified for confounding. However, here we actually do want to derive things like confidence intervals, standard error estimates, and p-values to use in interpreting the potential effect of mediation. For example, the mediated effect through that indirect pathway. So, like before with confounding, we do have this relationship between our models where the difference of the x variables crude and adjusted estimator will be equal to the value of gamma hat x for the covariate model times the effect of the mediator from the adjusted model. With this information, Sobel in the past has derived the standard error for this difference of the crude and adjusted estimator, or the gamma hat x, beta hat m product, by using the delta method. And we'll touch on that at the very end of the slides with just a brief note. But essentially it gets us to this equation here, where we take the square of the beta coefficient estimate times the variance of the other estimator from that product of gamma hat x times beta hat m. Oftentimes, though, we actually are interested in summarizing the proportion or the percentage mediated by our variable m, and we do so by taking a ratio of the indirect effect divided by the total effect we measure. Here we just, for that total effect, we divide by beta hat crude, and we can either use either of those two definitions for the indirect effect calculation. If we then multiply that by 100, we have a percent mediated instead of the proportion. So as I mentioned, we're oftentimes interested in using things like a confidence interval and a p-value to actually describe the significance of that indirect effect. Much of these formulas are pretty similar to things we've seen before, just with slightly different notation for our context of mediation. For example, the 95% confidence interval around our indirect effect we'll take the estimate of our indirect effect, the product of gamma hat x times beta hat m, for example, plus or minus some critical value. In this case, we might assume normality and take the z standard normal distribution. And then we'll multiply it by the estimate of the standard error or the variability of gamma hat x times beta hat m that we showed on the previous slide. And then if we're interested in showing this on the proportion or percent mediated scale, we'll see this in an example later, but we just simply divide this estimate by the total effect. Then if we're interested in getting a test statistic and a p-value, again assuming approximate or asymptotic normality, we can calculate a z statistic as the indirect effect divided by its standard error estimate, and a p-value can then be derived based on this value for the z statistic by referencing the standard normal distribution. Let's now turn towards an example of mediation and see how it works in practice, and also some things to be aware of that could happen that we might need to watch out for. In our example, a study was performed to examine if a weight loss drug could cause a decrease in the systolic blood pressure of adolescents who had severe obesity. This drug was already demonstrated in adults, so there was a hypothesis that it might be beneficial. It was also hypothesized that changes in BMI, though, would account for the decrease in blood pressure observed in the subjects on the study drug. So there was an interest in identifying how much of the effect might be due to the drug and how much of the effect might be due to the fact that maybe they're losing weight and their BMI is decreasing. In all, 21 adolescents were randomized, 9 to the treatment group and 12 to the control group. The data we'll be leveraging and using today includes a group indicator variable, treat group, where 1 is equal to the drug or intervention group and 0 is the placebo, a change in BMI variable, and a change in systolic blood pressure variable over the course of the study. In this case, if we were thinking of drawing out our DAG, we would have something that looks along the case of the drug going to affect the change in systolic blood pressure, but we're wondering if that change in BMI might be our indirect effect. And so here's what we might look at for an example of what our DAG, or flow of information and causal framework, might be in this case. Let's start by walking through our 3 models step by step before tying it all together. So first we fit the Crude model, where we have our outcome of the change in systolic blood pressure with the only predictor being our treatment group indicator variable. Here we see that there is, from our model fit, an 8.97 millimeters of mercury greater reduction in systolic blood pressure in the treatment group compared to the control group over the course of the study. This then, based on our p-value from the coefficient table, represents a significant difference between our 2 groups. A follow-up question we may wish to ask or evaluate would be, is there the chance that confounding could have occurred in this study? Now, the general answer is it's always possible, but here we wouldn't expect it to be likely because the groups were randomized. So by randomizing individuals, we would expect factors to be balanced across groups in theory or on average. Now let's take a look at the adjusted model if we add our mediator, the change in BMI over the course of the study, as one of our predictors. Here our interpretation is that of our primary explanatory variable of interest is that after adjusting for the change in BMI, there is now a 4.55 millimeters of mercury greater reduction in systolic blood pressure in the treatment group compared to the control group. However, this difference is no longer significantly different from 0, with the p-value being 0.476. From this information, though, from our first 2 models, we can start by estimating the indirect effect from the beta hat crude and beta hat adjusted estimators, where we see that our indirect effect from those 2 estimates is negative 4.4268. We can also verify the indirect estimate by fitting that covariate model, or model 3, where we take our potential mediator, the change in BMI, as our outcome in this approach and use our explanatory variable of treatment group as the predictor. What we see here is that we get the same estimate of the indirect effect of negative 4.4268 by using the information from this model that we saw from models 1 and 2 as well. In the context of mediation, then, this indirect effect would be the extent to which we believe the outcome, the change in systolic blood pressure, changes when the primary explanatory variable of treatment group is held fixed, and the mediator variable, the change in BMI, changes by the amount it would have changed had the primary explanatory variable increased by 1 unit. or in our case, changed from treatment to control or placebo group. Now, of course, many times what we're actually interested in is the proportion mediated. So trying to tie it all together, we have our estimate up here of the general DAG or relationship of information with the corresponding estimators of interest that we may be interested in using. For example, from our indirect effect divided by the total effect, we see that we have an estimate that the proportion mediated is 0.4934. Or, for an interpretation in our context, 49.3% of the effect of the study drug on changes in systolic blood pressure is mediated through or can be explained by changes in BMI. So in other words, if the drug causes a change in weight loss, then it may actually be the fact that the decrease in BMI is accounting for some of the improvement in systolic blood pressure and not just the treatment on its own. However, we do note that we can actually do inference on this estimate, and we can walk through the steps to do so here. So the first thing we need to do is to calculate the standard error using that equation we saw previously, which does connect the standard error estimates for the coefficient from the appropriate model with the beta coefficient estimate as well. We see by taking that information from models 2 and 3 previously and plugging them in here, we then get an estimate of the standard error for our indirect effect being 5.277. Using this information, we can calculate a test statistic for z equals to negative 0.839, and with that information we can calculate a two-sided p-value for the test where p is equal to 2 times using then p norm in R to get a p-value of 0.4015. In other words, here we would say that p is greater than 0.05, so it seems like we're going to have an insignificant or not statistically significant effect of the proportion mediated. However, we can also calculate the confidence interval and introduce some other considerations here. Calculating the confidence interval for the indirect effect at the top, we see that we plug in the estimate for our indirect effect, our critical value based on the normal distribution, and then the standard error we calculated on the previous page. We see here that we have a pretty wide interval that goes from negative 9.7 up to positive 0.85. However, we also many times are interested in transforming this or translating this to the proportion or percent mediated scale. And so here in this context, we would have a proportion mediated between negative 0.095 up to 1.082. Now, what this represents is an inconsistent mediation model. And we'll discuss a little more what that means on the next slide and some reasons why it may have occurred here. But we can still interpret this in the context of the results we have, that the change in BMI is not a significant mediator of the relationship between treatment and change in systolic blood pressure because p equals 0.401. This is the case even though it explains 49.3% of the effective treatment in our sample, or a negative 9.5 to greater than 100% of the treatment effect. Now this leads us to this concern or consideration for inconsistent mediation. What we've discussed so far in this framework we've presented in class today is one of the most basic formulations of the mediation framework for hypothesis testing, sometimes called Sobel's test by the investigator who derived the properties for that delta method and our confidence intervals and p-values. However, there are increasingly more complex approaches that could be used and may be more appropriate for different situations, although we will not explore those in the context of 611. For example, it is possible with inconsistent mediation here at the forefront of our mind that our simpler approach could arrive at a proportion mediated that is either itself negative or greater than 100%, or has a confidence interval that includes either of those ranges. This can occur when we have what we call an inconsistent mediation model, where at least one mediated effect has a different sign than the other mediated or direct effects in the model. Another double whammy in our case here for our example is that the proportion mediated may also be unstable for sample sizes that are under 500. In our case, we only had 21, and so 21 being much less than 500 may suggest that we don't want to put too much stock in this model as the end-all be-all conclusion. So with that, let's touch on a few extra notes to keep in mind. The first is the derivation of the standard error of the indirect effect. We're not going to delve into too much detail, but I feel like it's worth noting how Sobel got to this estimator that we're using. For any random variable x, we have this approach called the delta method that you will learn about in statistical theory coursework. But it can be used to derive the approximate variance of a function of a random variable. So for example, we wrap our random variable x here in some function f of x. The delta method suggests that, for instance, the variance of f of x is equal to the first derivative of that function, f with respect to x squared, times the variance of that random variable x. How is this variance derived in practice then? Well, from calculus, we can note the first order Taylor series approximation of a function f(x) that is expanded around mu its mean would be equal to this in that first order Taylor approximation. The variance then of g of x, the function of x, can be estimated further using this equation and property here, or we can say it's approximately equal to g prime mu squared times the variance. We also can note that the variance of k random variables f of x can be approximated as well through this relationship of the variances and the covariances, in the case then of tying in the delta method as well of our derivatives of the first order for those given models. Ultimately, we're not going to delve much more beyond this very brief overview of the approach, but Sobel used this to derive that standard error estimate that we used earlier. One other consideration to keep in mind is that instead of using this normal approximation derived by Sobel, is that we could use bootstrapping. This is something we discussed earlier in the semester, but remember, it makes no distributional assumption, and it could potentially produce more accurate estimates of our confidence interval, especially if we think normality might be violated. However, bootstrap sampling is based on our original sample, so it won't correct for potential instability of the estimated indirect effect if we have a small sample, for example, less than 500. And so we still could end up with an inconsistent mediation model and an estimate of the interval, but at least we don't make those distributional assumptions. And so with that, we're going to wrap up our discussion of mediation models and variables, noting this connection of the roles variables can play from confounding to precision variables to mediators, and we'll now expand into some ideas relating to interaction terms in a model and polynomial regression modeling.